Okay, looks like we are now live. So, hello. This is another wonderful session of J Champions Conference.
Wonderful.
Yes,
It's going to
wonderful,
be wonderful.
fantastic.
Yeah.
So I'm just moderating. I'm Keto, and I'll just be here to relay any questions to Barry. So, Barry, take it away.
Yeah. Type in any questions at any time, and I've given Keto instructions to stop me in the middle of a sentence
Yes,
if a question comes in, because I like questions. Um,
yes.
so I'm going to click the present button and share screen, and yes. And which one do I want? I want that one. And now what you're going to see is a bunch of crazy stuff until I pull up my PowerPoint slides. And there are my PowerPoint slides. Keto, is everything cool there? You can see the slides? Hello, Keto. Oh, I can't hear him.
Yes. I can.
Okay.
Can
All right.
listen.
Okay.
Sorry.
All right. Yeah, that's fine. Okay, let's go here. Java and the promise of quantum computing. It's about Java and it's about quantum computing. Hey, right? I don't know when it was, but during part of the last century, somebody said, someday there will be 1,000 computers in the world and no more. And wow, okay. I've got 4 or 5 of them in this room if you count my watch and so on. Quantum computing is on its way. And even though it's not here yet, it's going to be within most of our lifetimes. So we really should get ourselves going on here. And let me introduce the whole topic. Oh, by the way, I am Barry Bird. I work for my day job at Drew University in Madison, New Jersey, a fine liberal arts college in northern New Jersey. I'm the author of Java for Dummies and several other Java books. Um, and I'm working on a quantum computer book right now. But in the meantime, right, let's come and thank Johann Voss. Johann created the Strange API, the Strange SDK. And Johann's work is what it brings me here today, because what he did was he created a Java based way of communicating with quantum computers. Every time I do this talk, I begin by thanking him profusely for sharing his materials and for sharing the opportunity to present them to various groups. So go out right away and buy Quantum Computing in Action by Johann Voss. It has all the material that I'm going to talk about today and much more. Good stuff, good stuff. That's what a quantum computer, what some kinds of quantum computers look like. Um, this is, I think, an IBM version. They take this entire thing, they sink it into a huge vat, and then they supercool the vat to maybe a degree above Kelvin or a degree above absolute zero Kelvin um, or less. And the um, the qubits itself, the real computing part, the processing part, is that thing at the very bottom, that little golden disk at the very bottom. The rest of it is just sort of accessories to get that little golden disk to work. And outside of the cylindrical vat into which this is dipped, there are going to be lots of classical computers to monitor and run this thing and get it going. If you've got a couple $1 billion, you can probably make one of these yourselves. Otherwise, you'll probably have to wait. Um, I don't know if you're aware, but there is this thing called quantum supremacy. And quantum supremacy will exist when we have quantum computation that can outrun classical computation. Classical computation is the kind that you have right in front of you, the kind that you have on your watch, the kind that you have on your phone. Quantum computation takes advantage of the weird properties of the quantum world in order to solve problems. And they can theoretically solve problems in seconds that would take 10,000 years to solve. 100,000 years, a million years. Um, Google in October 2019 claimed that it had solved a kind of a toy program in 200 seconds with its quantum computer that would have taken 10,000 years for a classical computer to solve. A group in China said they solved it on a classical computer in 5 days. Okay, 5 days, 10,000 years, let's not quibble. The quantum computer solved it in 200 seconds. You got to call that an improvement. Um, but real quantum computing, effective quantum computing, is years away. Um, Last December, a group of researchers in China claimed that they broke today's encryption with a quantum computer and only 372 qubits. Again, it remains to be seen how this will have ripple effects or to what extent they may have used various other techniques, but we'll see where that goes. Um, every day I hear about different announcements where they've got bigger and better quantum computers beginning to approach usefulness, or at least on the way to approaching usefulness within the next few years. Quantum key distribution, that's a way of distributing secret keys in order to do conventional encryption in which you're pretty much guaranteed that the distribution of the keys is secure. You don't actually send a key from one computer from the sender to the receiver. You actually have them both create the key on their own using quantum techniques. So this stuff is coming along. Companies such as the ones listed on the slide are working on it. There are billions of dollars being spent by governments and by companies to get this going. It's on its way. So, what I want to do today is kind of introduce a few quantum computing concepts and show you how Johann Voss does it in Java. Let's march. Okay, give me a sec now. I need to do, oh, there we go. Okay, good. All right, and now I'm going to have to change my pointer options to uh, pointer options. Okay, there we go. All right, quantum computing now is on the level of single qubits. Think bits, but qubits are a little bit different. In classical computing, a bit is just 1 or 0. And I'm going to click a button here. And you see, if I send you a 0, you'll receive a 0. The fact that the 0 in this slide is coming in and out, popping in and out, is to kind of illustrate if I sent you a bunch of zeros, then if it was a clear channel or a reasonable channel, every time I sent you a 0, you would see a 0. And if I sent you a 1, every time I sent you a 1, you would see a 1. And that's the way the classical world works. And, oops, okay, we're going to do something different here. Okay. And the classical world, at the very heart, works with gates, logic gates, the AND gate, the OR gate, and the NOT gate. The AND gate outputs a 1 if both of the inputs are 1. The OR gate outputs a 1 if either of the inputs or both are 1. A NOT gate reverses whatever it gets in. So, we've got this gate logic in conventional computing. And in Johann's version of quantum computing with the Strange API, we can do gate level logic. And this program that you see in front of you is gate level logic. Let me give you kind of a tour of it. I'm going to go back to pointer options, laser pointer. And so what do we got here? We've got a simulator. That's the device on which we will run our quantum computer program. And we're also going to declare the existence of a program. This number 1 here indicates, believe it or not, that this program will have only 1 qubit. The equivalent in the classical world would be a program that involves just one bit. Crazy, right? It's less than a hello world program. It's just one element that's going to be, when we measure it, either 1 or 0. So as part of the program, what we're going to do is add a step in the program, and I'll show you that in a minute. A step is just kind of one instance of a gate in this case, and I'm going to put an X gate onto my um, onto my um, qubit wire, and then I'm going to add that step to the program. Okay. After that, I've got some statements in which I measure the result. So if I create a new program with a single step and a single gate on that step, this gate is a NOT gate. It goes on 0, which is the initial qubit, the only qubit that I've got. And what that gate is going to do, the X gate, that's a NOT gate, that's just going to change it from a 0 to a 1. Everything's going to start off as 0, and in this case, with an X gate, it's going to end up as 1. It's going to be a very, very, very tiny program. Let's take a look. I'm going to run it for you just so that you see what this does. I'm going to come down here, and I'm going to run polyx, and here we go. Yeah, let me bring the result into view. So what I've got here, and I'm going to make it larger so that you can see it. Keto, can you tell by doing what I just did, does the screen enlarge? Or does your view of the screen enlarge?
Yes, it does.
Very good. Okay. All right. So I just typed a command to run the program. And what I've got now here is the 0th qubit. Well, there's only a 0th qubit, there's nothing else. The qubit starts in the 0 state because by default, all of them do. It goes through an X gate and goes to the end where it gets measured. And this word on indicates that what it reads after having gone through that NOT gate is not the 0 value, but instead the 1 value. In this world, on means 1, off would mean 0. Wow, you couldn't have a simpler program. I guess you could have a simpler program if you didn't have an X gate. But anyway, that's all this program does for now. Let's take a look at these programs and the way they work in just a little bit more detail. So what I'm going to do now is create for you a program. First, I'm going to say, I want a brand new program, and that new program has 2 qubits. The fact that it has 2 qubits means that it's going to have a qubit labeled Q0 and another qubit labeled Q1. And they both start off in the 0 state. So I kind of have 2 wires with 2 qubits. And now I'm going to add to this program. I'm going to create a step in the program. And that step, it says step 0 right now. That step is going to become part of this wired diagram later. But for now, it's just step 0. And what am I going to do? I'm going to add gates to step 0. So in the strange programming API, I'm going to call step 0's add gate method. And what I'm going to add is a brand new X gate. And the 1 here indicates that I'm putting it on qubit 1, on the bottom qubit instead of on the top qubit. So now what I've got so far is a program with 2 wires, a step that's down here yet, and a call to add an X gate to the 1 level of step 0. Let me create a new step. How about that? Just to make life a little bit more interesting. I'm going to add step 1. So I've got step 0, I've got step 1. I'm going to add a Hadamard gate at level 0 to step 1. What is a Hadamard gate? A Hadamard gate is a gate that begins the quantum magic. A Hadamard gate is going to put this qubit into a state where it's neither 0 nor 1, it's something sort of in between all at once. And that's going to be an important feature for quantum computing. Let me just for fun add another gate. Over here, you see what I'm doing is adding a new Hadamard gate to the 1 level on step 1. That's down there. And then finally, what I want to do is take these 2 steps and put them onto the quantum circuitry. So I'm going to add another statement, and this other statement is going to be to call the program's add step method and add step 0 to the program. And finally, to call the program's add step method and add step 1 to the program. And now what I've got here is a 2-qubit piece of circuitry. What in the world can you do with 2 qubits? I mean, is it like having 2 bits in the classical world? Well, yes and no. It's pretty limited. But actually, when you add qubits to quantum computers, things build up pretty quickly. And let me show you how they build up. So, there we go. Remember that bits are either 1 or 0. There's a 1 down at the bottom, there's a 0 at the top, right? Qubits are different. A qubit can either be in the 0 state or the 1 state. If I throw you a qubit in the 0 state, then every time you catch it, you'll measure it as 0. So I'm throwing you 100 of them, and 100 times you catch my 0 and you look at it and it's 0. I'm going to do the same with a 1 qubit. I'm going to manufacture a 1 qubit. I'm going to throw it to you. You're going to look at it. You'll measure a 1. You'll see a 1. That's why I've got the 1 blinking there. But you see, if I apply a Hadamard gate to a qubit, then sometimes you'll see a 0 when you catch it and measure it, and sometimes you'll see a 1. So it's kind of half in the 0 state and half in the 1 gate. Now, let's be clear. You won't be able to do this over and over again with 1 qubit. What's going to happen is I'm going to manufacture 100 of these, or maybe 1,000 of these, or maybe 1,000,000 of these. And I'll do them by adding a Hadamard gate to my circuitry. So I start with a qubit in the 0 state. I put a Hadamard gate on my circuitry. I send my qubit through the Hadamard gate. It goes into this half 0, half 1 state. I manufacture 100 of these, and I toss 100 of them to you. About half the time when you measure them, you'll say, oh, I just got a 0. And about the other half of the time, when you measure them, you'll say, oh, I just got a 1. You'll never be able to perceive that it's in the half and half state. That just doesn't happen in nature. And in fact, the theory says that the qubit that I send you that's in the half-half state will not be 0 or 1 until you catch it and look at it. It's the observation that turns it into 0 or 1. But anyway, let's skip ahead a little bit and think of what the consequences of this are. Let's say that I have 3 classical bits, and let's say they're 101, binary 5. 3 bits, what does that mean? That means one thing. That means 5. Okay, that's just one thing. But let's say I have 3 qubits. Well, the first one is in the half 0, half 1 state. The second one is in the half 0, half 1 state. The third one is in the half 0, half 1 state. This thing could be any of the possible combinations of 3 zeros and 1s. So this thing kind of has the properties all at once of being either binary 0, binary 1, binary 2, binary 3, all the way up to possibly binary 7. So if I want to do calculations on 8 different numbers all at once, I could do it with this combination of 3 qubits. If I want to do calculations with 64 gigabytes worth of numbers. 64 gigabytes, that's what I've got in this laptop. That's a lot of gigabytes for RAM. All I need is 40 qubits. If I have 40 qubits and I have the right kind of manipulation of these qubits, then I can do in supposedly 1 or 2 steps, zap that set of qubits and do what I would be able to do with 42 gigabytes of data at once in a classical computer. Now, I'm not going to lie to you, manipulating and managing and orchestrating 3 qubits at once or 10 qubits at once or 40 qubits at once is not easy, and it's not straightforward, and it involves quite a bit of math. But the promise of this is that we can learn to build the hardware that has many, many, many qubits at once and create the algorithms that can manipulate them so that we can come up with answers that we would never be able to come up with classical computers, because classical computers would take 10,000 years, millions of years, whatever. That's the promise. The unfortunate unpromise is that as soon as a malicious agent gets this capability, they'll be able to break the RSA encryption scheme in seconds, and some other encryption schemes too. So, I mean, it's got its good points and its bad points. Yes.
So that brings up a good question from Victor that he brought up earlier. So,
Okay.
so he says, are we all going to be in trouble when they double the qubits and decrypt our bank passwords?
Yes. Unless unless we come to grips with what's called post-quantum cryptography. Now, post-quantum cryptography, there's an agency of the government right now, the U.S. government, that's been taking proposals for cryptographic schemes that cannot easily be broken by quantum computers. And right now there are 4 proposals. They're all being analyzed and discussed, and probably more than one of them will survive the final rounds. But there are schemes that are better than RSA and cannot be broken by quantum computing. And what's nice is that people are working on them now instead of, when Boris Badenoff finally gets himself a quantum computer.
Right. Okay. So Victor has one more question.
Sure.
Does Johann's book cover the math for those of us who need a refresher on Hadamard and some linear algebra transformations?
Johann's book does a nice job with this. It covers enough math so that you can follow what's going on. It doesn't cover so much math that you're drowned in math details.
Cool. All right. Thank you.
Okay. So let's see what we've got here. Oh, everybody usually asks me, how do you build a qubit? I am not a physicist. So I basically know that there are a bunch of different technologies to do it. If an electron is spinning in one direction, that's a 0. If it's spinning in the other direction, that's a 1. There's another way you can polarize light beams. So a light beam can be vertically polarized or horizontally polarized, right? 0, 1. And if a light beam is polarized this way, we're going to think of it as a 0. If it's polarized that way, we're going to think of it as a 1. If it's polarized at a diagonal, we may be thinking of it in this half and half state. It gets complicated, but that's basically the idea of how we make qubits. And there are engineers who, I would say they know 1,000 times more about this than I do, but 1,000 times more about this than I do is 1,000 times 0. So let's not phrase it that way. Okay, I'm not going to do the block sphere.
So
I will. Yeah.
One more question for you. Vincent says qubits are the solution to Moore's law dilemma.
Oh. super, super, super solution. Um, I hope we have other solutions before then. Um, I mean, you're not talking about Moore's law dilemma. You're talking about essentially giving computing superpowers. Um, Moore's law would just be what, doubling every 18 months?
Yeah.
No, this would just boom, crash. Um,
All right. Cool. Thanks.
okay, all right. Let's do a Hadamard program. So I'm going to run this code. Um, we create a program with just one qubit. We create a step and we put this one magic Hadamard gate on the step. And then we add the step to the program. Let's just see what happens when we run this. So there's the Java FX code or Java FX output. Again, this is just being run on a simulator right now. So this is just a classical computer. You know what? It's my laptop. Just saying, what would I do if I were a quantum computer? How would the math work out? But if we take this and we compile it for a real quantum computer, then we have a real quantum computer doing what it should do. And there are definitely real quantum computers where you can run code like this now, as long as you don't ask for too many qubits. So let's see what we've got here. Down at the bottom, maybe I'll do my, right? This thing ran this circuit 1,000 times and got 518 zeros and 482 ones. That's about half and half. Okay. And that's what you get with quantum computing. You get about half and half. You don't get exactly half and half. And you certainly don't get them in lockstep alternating order. Here's what the circuit looks like. That's produced by Java FX. And the 50% there means about half the time you're going to get 0 and about half the time you're going to get 1. So now what I'm going to do is run this again. Remember these numbers, right? 518 and 482. You don't have to remember them too precisely. Just remember that we're not going to get the same thing when we run it again. Yeah, so this time we got 497 and 503. And that's the way quantum computing works. It's not deterministic. We're going to get different numbers every time we run a program, and then we're going to do statistical analysis. We're going to tune our algorithms so that we have a very, very, very high chance of getting the right answer, the answer that we're looking for. But some tuning is always going to be required. It's not the kind of thing where hey, my program is off by 1, it's not working. Quantum computing doesn't do that. So let's see what we've got next here. Yep, there it is. Okay. In this run, it was 507 times and 493 times. And I'm going to skip those slides and march on to entanglement. So this is one of the weird features of the quantum world.
Before you get to that, one more question for you.
Sure.
JT says, will quantum computing make Bitcoin or any crypto easier to hack?
That's a good question, and I don't know the answer to it. I'm going to take I see. Here's one of the problems with quantum computing algorithms right now. If you give me a reasonably straightforward and well-defined problem in the classical world, I may say, "Wow, for practical purposes, that's hard to write code for." But conceptually, at least to get a brute force solution, it won't be a difficult task. So, you hand me a problem in a technical interview, and it's some convoluted thing where I have to, rearrange this or do that. Um, there's a solution, and given enough time, I'll think of it, and even given more time, I'll be able to write it down. And if it ends up having to be a million line program, well, you just chug away and chug away and chug away until you get all the pieces of it put together and you're in good shape. Quantum computing doesn't work that way. For quantum computing, there isn't a clear mental path on which you can solve problems. The solution to a problem is a tricky manipulation of mathematical concepts. And we've found tricky manipulations for some problems and not for others. And so the number of quantum computing algorithms that we have is limited right now, and it continues to be limited by virtue of the inventiveness of very clever people to come up with these schemes for making the quantum world work in parallel with whatever problem we're trying to solve. I'll show you some examples of that soon. That's my not so short answer to the question about Bitcoin. I don't know because, you know, some problems are solvable, others, there's just no algorithm to do it. And thinking of an algorithm is the work of some genius people. Okay, let's try some entanglement tricks. Now this is weird. And if I think about the name of Johann's software, which is Strange, the Strange API, um, this is probably where strangeness comes in most. This is the strangest thing that we know about. Um, you've got two qubits. Call them qubit A and qubit B. They're both in state 0. And you apply this Hadamard gate to one of them, so that one of the qubits now is in the half and half state and the other qubit is still in the 0 state. Now what you do is you apply a multi-qubit logic gate that does the following. It says put qubit B in the 0 state to the extent that qubit A is in the 0 state. And put qubit B in the 1 state to the extent that qubit A is in the 1 state. And that's a mouthful. That's the people who really do this work would yell at me for the way I just phrased it. But the idea is you take qubit A and you have it impose its zeroness or oneness on qubit B. And that's called entangling. Oops, let's go back. There we go. There's entangling. So the two qubits are entangled. And that means they're married, right? And like all married couples, they want to take separate vacations. So we keep one of them on Earth and send it to a lab, and the other one we send to the Cygnus constellation far away in the galaxy. And now qubit A was Hadamarded, so it's half and half. Qubit B was sort of linked to qubit A in its Hadamardness. So they're both in the half and half state. And now qubit A is on the Cygnus galaxy, far, far away, and Cygnus galaxy, Cygnus constellation in the galaxy, and qubit B is here on Earth in a lab kept by Price Waterhouse. So now what we're going to do is some three-headed being on the Cygnus galaxy is going to make a measurement of qubit A. So when they do that, since qubit A is in the half and half state, it's going to see either a 0 or a 1. Let's say for the sake of argument that the Cygnesian sees a 1. Well then, instantaneously, if need be, if a being in the lab on Earth measures qubit B, that person will see a 1 also. These two qubits are entangled, which means that whatever we measure, whatever we get when we measure qubit A, instantaneously becomes the same thing that we measure when we get qubit B. It doesn't matter how many light years apart they're spread. And you may say, well, Natch, when qubit A and qubit B were together, they were linked and they told each other, hey, when we're measured, we're going to be in the 0 state, or when we're measured, we're going to be in the 1 state. But it's been proven by an extremely clever argument that that is not the case. Until qubit A gets measured, both qubits are in the half and half state, and not even nature knows what they'll be measured as. So qubit A and qubit B are linked in a way that makes it so that the measurement of one instantaneously snaps it into the 0 or 1 state, and instantaneously somehow gets communicated light years away to the other one. It's really bizarre. And if you ask me, do I understand it intuitively? The answer is no one on earth understands it intuitively. That's why there are different interpretations of quantum mechanics. And by the way, maybe on the planet Cygnus, the three-headed being knows what's going on, but we can't talk to them, so we can't find that out. But now, anyway, once we've got this superposition, that means that 3 qubits can represent 8 values, and 40 qubits can represent 64 gigabytes of values. And now to orchestrate this thing, we have qubits that are tied together, linked together, and when we manipulate one of them, we know how the other one will turn out. And that's how all this works. That's how all this comes together. So let me jump now to, let me just illustrate the Bell State program in Java. I'm going to create 2 steps, step 1 and step 2. To step 1, I'm going to add a Hadamard gate at level 0. That's up here. To step 2, I'm going to put a C NOT gate, a controlled NOT gate. And that's pictured right here. You can see my pointer, right? Just yell if, Keto, yell if you can't see my pointer. Okay, I'm going to assume that you can. This C NOT gate, what this does is it sort of conditionally changes Q1 to a 1 to the extent that Q0 is a 1. So Q0 is in the half-half state. Q1 gets changed to a 1 for the part of Q0 that's a 1. It's kind of crazy. But anyway, when we end up measuring these at other ends of the galaxy, we get that either both of them are 0 or both of them are 1. I feel compelled to demo it. Every Java talk has to have a demo. And here we go. Well, there it is. Okay. Same thing that's on the slide. And the strange API gives us the ability not only to draw the circuit that we created, but also to display the results. Now, if this were a real quantum computer, then there'd be some 0 1s here and some 1 0s, because real quantum computers are noisy. Right now, we're in what's called the NISQ stage, NISQ, noisy intermediate stage quantum. We don't have a lot of qubits yet, and we have some noise. So we won't always get exactly 0 0 and 1 1 here. We'll have a few 0 1s and 1 0s. But that's life in the big city. So let me just march on here. and give you an idea of what a quantum algorithm looks like. And then with the remaining few minutes, I'll tell you a little bit about breaking the RSA algorithm. So let's consider a problem in which we want to find one thing from among 100 things. So this is a search algorithm that we want to do. So I go to a dark alley and somebody hands me a component and says, if you apply this component to 100 qubits, it will mark one of those qubits. And I expect you to find out which of the qubits it marks. Okay, here's a picture of that. Find the red circle, right? Somebody gives me a black box and says, which of the inputs that you feed this thing will come out red instead of blue? And if I've got 100 possible inputs, then it might take 100 steps with a conventional search. But Grover's algorithm does some quantum magic and it ends up taking only 8 steps. So, I mean, this is fairly unintuitive. How can an effective search of unordered data, this is not, you can't do a binary search on this, it's just, yeah, right? How can you evaluate what this chip does, what this component does, by running it only 8 times? That's kind of bizarre. There's a strategy, and the strategy is interesting. What I'm going to do is start by illustrating it for only 4 possible values. So let's say now somebody hands me a chip and they say there are 4 possible inputs to this thing. And when you put those 4 possible inputs through it, it's going to mark one of them. So you can put in 0, 0 and it won't mark it. You can put in 0, 1 and it won't mark it. You can put in 1, 0 and it will mark it. And you can put in 1, 1 and that won't mark it. So classically, you have to check what it does to 0, 0. You have to check what it does to 0, 1. You have to check to see what it does to 1, 0. Aha, you can stop there because you found it. At the worst case running time, it's going to take 4 applications of this component. On average, it's going to take 2, whatever. I'm marking these with the numbers 1/2. And 1/2, if I square it, I get 1/4. And 1/4 is the probability of seeing this combination of qubits versus this combination versus this combination versus that combination. So there's a 1/4 chance if I measure these qubits that are in a superposed state of seeing them as 0, 0, 0, 1, 1, 0, or 1, 1. And the halves here represent that 1/4 possibility. You have to square the number half. So it's probability 1/4. That's what I've got. And this minus sign, this is what's called a phase change. And that's what my circuitry does to this. So I'm going to take 2 qubits. I'm going to Hadamard them both independently. I'm going to send them through this circuitry that this mysterious stranger gave me a dark alley. And when I send them through, if they're in the 1, 0 state, then they're going to be marked with this phase change. Think of 2 waves out of phase. That's what this circuitry is going to do to these things. I realize this is a little bit strange, but that's kind of the best way I can explain it. So how am I going to find out in just one step which of these is marked with a minus sign? Well, I'm going to start with 4 qubits, each of which has this 1/2 bit. Not 4 qubits. I'm going to start with 4 possibilities. The 4 possibilities being 0, 0, 0, 1, 1, 0, 1, 0. Each of them with this 1/2 in front of it. I'm going to run it through the circuitry. And when I do, it's going to mark one of the qubits and put a minus sign in front of one of the qubits. This is all physics. I mean, this is what happens with this circuitry. And how am I going to determine in just one step which one of these is the minus 1/2 one? I can run this through some gates. And by running it through some gates, I can determine where the average of those 4 numbers is. The average of 1/2, 1/2, 1/2, and minus 1/2 is 1/4. And when I run it through more gates, what that's going to do mathematically is it's going to tilt this thing, it's going to rotate this thing around that pivot point. So it's going to do that. And now you notice that what I've got is probability 0 of seeing any of the states that weren't affected by this mysterious component, and probability 1 of seeing the state that was affected by this component. Now, there's a lot of stuff going on here that I'm not explaining, so I don't blame people if they feel like, oh, this is really vague. But that's basically the way Grover's search algorithm works. You put things in all these strange states, and then you do a rotation, a mathematical rotation with the gates. And then once you're done, there's a high probability that when you measure the system, what you'll see is the state that was put as an outlier, that was given a -1, 2. Let me give you one more example here. Let's start not with 2 qubits, a 0 and a 1, or a 0 and a 0. Let's start with 3 qubits. That means we have 8 different possibilities. And I've already applied my black box circuitry and put one of them into the negative state here. So let me apply my rotation. There's the average of all those 1/8 and that 1 - 8. And now I rotate. Mathematically, I do get a gate that rotates. And now you see when I measure this system, the probability that I see that particular state that was affected by the circuitry is closer to 1 than the others. It's all right. It's not quite where I want it to be. It's not 1. If I measure this system, right, there's a pretty good chance that I'm going to see this fellow here, but there's also a decent chance that I'll see any of these combinations over here. So let me try doing it again. Oops, there we go. That's not what I wanted to do again. Here's what I wanted to do again. I wanted to apply my mystery circuitry to this box again. The mystery circuitry, once again, takes that outlier state and puts it on the negative side of the graph. I'm going to find the average and do my rotation. And now when I do it, I have a very, very high chance of seeing the outlier. Close to 1, very close to 1. And that means that I essentially did my rotation in 2 steps. Well, actually, it was only 1 step because it was actually only 1 step that I applied my circuitry. I applied it once to get the outlier qubit to this side, and then I applied it one more time to get the qubit back to the left side. So I did basically 2 operations of this circuitry in order to discover, right, that a certain combination of 3 qubits was the outlier. Strange but true. Okay. Let me march on here because the killer app for quantum computing is Shor's algorithm. And so probably if you're familiar, well, if you're a Javateer, you probably know how cryptography works, how particular RSA works. It's easy to multiply 2 numbers together. It's very hard to factor a number. So if I give you 2 very large numbers, you can multiply them together, and boy, how boring that would be, but you finally get an answer, not difficult. If I give you a very large number, then finding out what 2 numbers they came from, particular what 2 prime numbers they came from, is probably intractable. It's probably not doable in polynomial time. And encryption schemes depend on this, the difficulty of factoring a large number in order to do asymmetric encryption, in order to be able to encrypt things so that all kinds of um, um, transmissions of messages are secure. So the question is, if you give me a very, very large number and I have billions of dollars to spend on a quantum computer, is it any easier to take that number and factor it into its 2 component primes? And the answer is yes, thanks to Professor Shor. We are going to just take a look at a tip of the iceberg of how that works. So let's say that the gigantic number that I'm going to use as my encryption key is the number 15. And at this point, you realize I'm being sarcastic. The number 15 is easy to factor, but let's just use 15 as an example. Let's say that the number that I'm trying to factor is the number 15. How does Shor's algorithm do that? Well, let's take the number 2 and let's calculate 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on. And then let's mod all those with 15. And when we get that, we notice a pattern. The pattern is that after 4 values, it goes back to 1 and repeats. And then it's going to go back to 1 again and repeat. And then it's going to go back to 1 again and repeat. So no matter what this number is, 15 or gazillion or whatever, if we pick a number here and we take it to the power 0, 1, 2, 3, 4, 5, 6, 7, eventually it will start repeating. In this case, it repeats with period 4. Now, the essence of Shor's algorithm is that there's a quantum computing way of quickly finding out what this repetition period is. With 4, it's no big deal, but with larger numbers, much, 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 much larger than 15, it's a monumental task for a classical computer. For a quantum computer, finding this number is rather easy. Shor's algorithm uses the quantum Fourier transform, and it's basically a way of taking a signal and parsing it into its component parts. It's a way of kind of fishing out the period here from all the numbers that we get in this chart. But let's take a look at what happens when we when we know the number 2 that we started up with here and the number 4 that we end up with from applying Shor's algorithm. Remember, somebody gives us the gigantic number 15 and we want to divide it into its component parts. What are we going to do here? Well, we're going to run Shor's algorithm on 2 and look at the number 4. We're going to take those two numbers and we're going to divide the 4 by 2 and subtract 1 from it. And look at what we get. We get one of the factors of 15. So the idea with Shor's algorithm is if you can find this number quickly, then you can find this number very quickly and find what might be one of the factors of the gigantic number like 15 that you've been handed. Now, I said might because it doesn't always work that way. There's another thing we can do. We can take the number 4 and the number 2, and after calculating 2 to the 4 over 2 power, we add 1 and we get 5. In this case, we're lucky because both the number 3 and the number 5 are factors of the number 15. We're not always that lucky. Sometimes just one of them is a factor of the number 15 or the number that we're starting with, the gigantic number other than 15. But one of them is going to be. And so the idea of Shor's algorithm is a very, very fast piece of quantum computing circuitry that doesn't have to calculate all these numbers. It just calculates this number quickly and uses it to find factors of a number like 15. Like I said, these algorithms aren't easy to come up with, but if we've got clever people who use the Java Strange API, when we've got some very fast working computers, I got a lot of slides here. Oh, look, this gets interesting. When we've got some very clever people who can program in Java and Strange, and we've got some quantum computers that can handle this, it's going to be a very different world. And that's what I have to tell you about Java and the promise of quantum computing. Keto, what do we got?
All right. Well, the first question is, can you give us the link to the slides, if you have them anywhere?
I don't have one yet, but
Okay.
I'll do something about that and make it public to the Java champions.
Okay, cool. Another one is if we go back to your slide when you were talking about the CNOT gates.
Yeah.
The question from, I'm sorry, I'll butcher your name, but the question from one of our wonderful audience members was, what if we add a third wire and make a CNOT 1, 2
and make a CNOT what?
Angle. CNOT, if it makes CNOT 1, 2 after CNOT 0, 1. So I think you had one CNOT gate on the slide.
Let me go back to that. Let me see if I can go back. Oh, okay. I have some extra slides here. CNOT. All right. So what happens if we add another CNOT after that? So I have to think about this for a minute. I should be able to tell you this immediately. I'm gonna share my slides again. The way that I normally do these calculations is by matrix multiplication. And it should be obvious to me what's going to happen there right now. but I don't. I'm gonna take a wild guess, and I think what's going to happen is what'll be changed will be um, nothing observable. I could be wrong about that, but what you've got up there at the top is 0, 1. It's going to take the 0. Yeah, it's going to reverse it, I believe, but in a way that is impossible to observe in nature.
Okay. Cool.
Yeah. But the usual way of doing this is to translate these gates into matrices and do the matrix multiplication, and then you can have an answer really
Fascinating.
quickly. Yeah.
Okay.
Other. What else have we got?
Victor asks, would Shor's algorithm work with conventional computers?
It would take forever. You can
So,
you can apply Shor's algorithm with conventional computers, but applying the logic of the quantum Fourier transform would take centuries.
okay. Hippolito asks, is it possible to have a wireless quantum network using entanglement?
Yes. The I mean, is it practical to do so? Um, an experiment in China took. Let's see if I can go back. Superposition and measurement, entanglement. Right. A group in China said, "How far apart is it practical to make these qubits with the technology that we have?" Now, I was talking about a lab on Earth for qubit B and a being in the Cygnus constellation for qubit A. We cannot send qubits that far because for various reasons. One of them is that they tend to decohere. They tend to lose the integrity of their state when they go very short distances. That's just the way quantum mechanics works. But what a team in China did was they sent a pair of qubits. They kept one qubit on Earth and sent the other pair to an Earth orbiting the other qubit to an Earth orbiting satellite. And the way they did that was wirelessly, with I think it was photons. So is it possible? Yes. Is it practical? I mean, ain't going to happen soon.
Right. Okay, I think that's all the questions we have.
Okay.
Oh, wait, I'm sorry. There's one more. Let's see if it pops up here. I just saw it on YouTube. Let's see if it shows up. Hey, there we go. All right. So Mark says, with entangled qubits, both sides just get to see the same random result simultaneously, but neither side can force a result, correct?
Right. That's correct.
Okay. So you can't really do communication. It's just...
Oh, yeah. Communication is an interesting story. You can teleport a qubit. So if I have a qubit in some weird state, then someone in the Cygnus constellation, I can get it so that a qubit of theirs is in exactly the same state. And it's done with entanglement. It's not by sending them a message and saying, hey, put your qubit in such and such a state. It's done by entangling qubits, taking my qubit and keeping it and sending an entangled qubit to the Cygnus constellation, and then doing some other manipulations that kind of destroy my qubit, but make the Cygnus qubit suddenly be in the same state that my qubit's in. So communication, yes, communication of a sort can happen. Now, it's instantaneous in one way. When you destroy my qubit, then in a certain theoretical way, the other qubit snaps into the same state that my qubit was in. On the other hand, I do have to send some classical information to Cygnus in order for them to know how to interpret what is going on with their qubit. So it's a weird story. And quantum networking means using that feature, teleporting qubits so that, right? Or
Right.
teleporting Captain Kirk.
Okay, cool. All right, so there's a little bit of a chat going, but I don't think we have any other questions. You got a few very knowledgeable people in the audience, so it's cool.
That's good.
All right, well,
Okay.
thank you, Barry. Great talk.
And thank you so much for moderating. And again, thank you to Johan. Thank you, thank you, thank you. And thank you to the audience. Love it.
Yes. Thank you so much for coming to J Champions Conf. And of course, there'll be more great sessions today and tomorrow. All right. Thank you, everybody.